there are 4 control and status registers that need to be examined on a privilege switch. These CSRs provide information on the event causing the privilege switch. The cause CSRs record the reason an interrupt or an exception occurred. The high bit in the cause CSR tells us whether it was an interrupt or an exception that caused the privilege switch. The remaining bits encode the specific cause. The MEPC and the SEPC CSRs hold the program counter of the instruction that was interrupted or the one that caused the exception. During a return from the trap handler, the MRET or the SRET instruction is executed, and the execution will resume at the address specified in the MEPC or the SEPC CSRs. The MEDELIG CSR determines at what privilege mode the exception is handled in. The MEDELIG CSR has a bit corresponding to each exception code. If the bit corresponding to the exception code is cleared, that implies there is no delegation and the exception is handled at the machine mode level. The target privilege level in this case is machine mode. On the other hand, if the bit corresponding to that exception is set, the exception is delegated to the next privilege level, which in this case would be supervisor level. The MTVEC and the STVEC CSRs determine where the control transfers when an interrupt or an exception occurs. These registers hold the trap handler base address. They also encode whether the trap vectoring mode is direct, which implies a single entry point, or vectored, which is a per interrupt entry point for interrupts. This diagram captures the processor actions on an interrupt or exception. When a program running in supervisor mode executes an eCall instruction, the processor begins its standard trap entry sequence. The first question the hardware answers is who should handle this exception, supervisor mode or machine mode. That decision is controlled by the MEDELIG CSR. If the bit corresponding to the exception is set in the MEDELIG CSR, the exception is delegated to supervisor mode. So the target privilege level is supervisor mode. If the bit corresponding to the exception is clear, then the target privilege mode is machine mode. Once the target privilege level has been determined, the processor then selects the appropriate trap vector register, MTVEC for M mode, STVEC for S mode, and updates the target PC. The target PC is the address where the trap handler will begin executing. It is the first instruction of the handler. Before transferring control to the handler, the processor must save enough state to allow a correct return from the handler. It first records the current privilege level in either the mstatus.mpp bits or the sstatus.spp bit, depending on which mode will take the trap. This also ensures that the trap return instructions used in the handler, either an MRET or SRET, will return to the correct privilege level. Next, the processor updates either the MEPC CSR or the SEPC CSR with the current PC, which is the address of the instruction that caused the exception or the interrupt, or the instruction that took the interrupt. This is the return address the handler will use when the trap is complete. With this bookkeeping done, the hardware now performs the final 2 steps. It changes the current privilege level to the target privilege level and then jumps to the trap handler PC taken from MTVEC or STVEC. At this point, the execution starts in the handler, which now has full context about what caused the trap and where to return afterward. Let us now explore the return from handler sequence. Once the trap handler has finished its work, whether it is machine mode firmware or the supervisor mode OS, the processor uses either the MRET instruction or the SRET instruction to return back to the interrupted program. The return sequence essentially reverses the steps taken during the trap entry, restoring the architectural state so that it can continue exactly where it left off. The first thing the hardware does when it encounters an MRET or SRET is to restore the previous privilege level. Recall that during the trap entry sequence, the processor saved the privilege level into MStat as MPP or SStat as SPP. Now it restores the saved privilege level from M status or S status depending on the MRET or SRET instruction, and it loads the target privilege level with that value. This ensures that the handler cannot accidentally return to an incorrect privilege level than the code that was originally running. Once the target privilege is restored, the next step is to recover the target PC. During trap entry, the hardware saved the return PC into the SEPC CSRs, SEPC or the MEPC CSRs. The trap return instruction now loads this value into the architectural PC so that the execution can resume exactly at the same instruction boundary where the trap occurred. Once the target privilege level and the target PC has been restored, the CPU simply changes the current privilege level to the target privilege level and the execution continues at the target PC. Let us summarize the privilege mode transitions with delegation turned off. Transitions from a higher privilege mode to a lower privilege mode use the trap return instruction of the higher privilege mode. In order to transition from machine mode to supervisor mode, use the MRET instruction with MStatus MPP pointing to the supervisor privilege. Similarly, to transition from machine mode to user mode, use the MRET instruction but with MStatus MPP pointing to the user mode privilege level. To transition from supervisor mode to user mode, which is again a transition from a higher privilege level to a lower privilege level, we again use the trap return instruction of the higher privilege mode, which is SRET in this case. And the SStatus SPP points to the user mode privilege level. In order to transition from a lower privilege mode to a higher privilege mode, use the eCall instruction. In order to transition from S mode to M mode, execute the eCall instruction in supervisor mode with the delegation bit for supervisor mode eCall turned off. Likewise, to transition from user mode to machine mode, use the eCall instruction in user mode with the delegation bit for user mode eCall turned off. What is the status when delegation is enabled? In this case, the supervisor mode eCall with delegation turned on stays in supervisor mode. The exception is delegated from machine mode to supervisor mode. So effectively, there is no change in privilege level. A user mode eCall with delegation turned on will have the exceptions delegated from machine mode to supervisor mode, and the user mode eCall will be handled in supervisor mode. This completes our discussion on Risc-V privilege levels. See you all in the next video.